Okay, so in this lecture, I now want to discuss some specific problems that employ the liquid-liquid extraction equations that we discussed and derived in the previous video. So in this example, we're going to start with a 50 mil aqueous solution of X. Okay, so this 50 mils is V aqueous, or in this case, the original phase in which the X is originally solvated to V1. And we're extracting it with an organic layer, diethyl ether. Recall this is a predominantly nonpolar organic compound. So volume organic or phase 2 is 10 mils. Okay, so originally this ether is pure. It's not containing any X. And X is going to reach some equilibrium where it originates in the aqueous layer. Some of that exits and enters the organic layer, and we get some K part or equilibrium constant. And that K part value, or the concentration of X in the organic layer relative to the concentration of X in the aqueous layer, we're told is 10-1, or it prefers diethyl ether to water 10-1, right? Which means that X is probably quite nonpolar, since it prefers to be solvated in the nonpolar organic diethyl ether phase. First question here, how many extractions with 10 mils of diethyl ether each time? So we're looking for N. How many are required to remove at least 99% of X from the aqueous phase? So recall that Q is the fraction of the solute X that remains in the original phase, or the water. So we want to remove, right, at least 99%, or we want Q to be less than or equal to 1%, right? In other words, in terms of a fraction, it's less than or equal to 0.01. So we can set up our Q equation here, right? Q is equal to volume 1 over volume 2 plus the partition coefficient multiplied by volume 2, all raised to the n number of extractions. And we are searching for this n number of extractions here. So Q, the largest it can be is 0.01. And the volume 1 is 50 mils of the aqueous solution. Over that same volume, I'm excluding the units because as long as we use the same volume unit, milliliters, this is just the unitless fraction, plus the partition coefficient times the volume 2. So if you want to solve this, right, we can now say 0.01 equals 50 over 150, or is equal to 1/3 raised to the n. And to solve for this exponent n, we need to take the log of each side. So you could say log or natural log of 0.01 over log or natural log of 1/3 is equal to n. Okay, so I took the log of each side and then isolated n. For n, you should get 4.2. And 4.2 indicates that you do 4 extractions and then 20% of a 5th extraction. But this is not possible, right? Our limitations are that we're working with 10 mil portions of diethyl ether. So we either do the diethyl ether extraction 4 times or we do it 5 times. And if you want to get at least 99% out, we're going to round n up. Or the only reasonable number of extractions to do to ensure that we remove at least 99% is 5 full extractions. or the total volume of the ether, the organic layer, would be 10 mils times 5. We would do 50 mils total consumption of ether. So the next problem, we're determining the concentration of X in each phase after that same 50 mil 0.1 molar aqueous solution is extracted with 10 mils of ether twice. So we do 2 extractions, or n equals 2. So to find the molarity in each phase, we need first to find the volume in each phase. And then, of course, you can say the molarity of X in the aqueous phase will be the moles of X aqueous divided by the volume aqueous. And that volume is 0.05 liters, right? Or we have 50 mils. The molarity of X in the organic phase is going to be the moles of X that have partitioned into the organic phase divided by the volume of the organic. It says we use diethyl ether, right, twice. That's the organic layer, 10 mil fractions at a time, and then we combine them. So this is going to be 0.01 liters first time, and then we're going to combine it with the other 0.01 liter or 10 mil fraction. So the final molarity of X in the organic phase is going to be the moles of X in the organic phase over 0.02 liters. Okay. So now we just need to find the moles of X in each phase, which means first, use the fraction equation. Find the fraction of X, Q, right, that remains in the water. So Q is equal to the volume of water over the volume of water plus K part times the volume of the ether raised to the n. Or this is equal to 50 over 50 plus 10. So K part was 10, we saw that. We were given that value up here where it preferred ether to water 10 to 1. And we're doing 10 mil extractions 2 times. So if you solve for this, you'll see that it's 1/3 raised to the 2 power, or 1/9. Okay, which means that 1 minus Q, right, or the fraction of X that is going to the organic phase, the ether, is 1 minus 1/9, or 8/9. So now we know the fraction of X in each phase. That was step 1. Or I guess we could say writing molarity equation step 1, finding the fraction step 2. Now, if we can just figure out what the total moles of X were in the beginning, we know that 1/9 of those total moles are now staying in the aqueous layer. And the other 8/9 have gone into the organic layer. So if we just know the total moles, we can use the fraction to find the actual moles in each layer. So the total moles of X. X originated only as an aqueous solute. It was 50 mils, 0.1 molar. Because it only originally was in the aqueous phase, I can use, right, the molarity. It was 0.1 moles of X per 1 liter of water. And we have 50 milliliters of water, or 0.05 liters. So only use the volume containing X originally. Don't use the other volume of the pure solvent. So 0.1 times 0.05 is a total of 0.005 moles of X. So from here, we can now find the moles of X in each phase. So the moles of X in the aqueous layer will equal the 1/9, because 1/9 of the moles remain, times 0.005. And the moles of X in the organic layer is 8/9 times 0.005. So if you calculate those values, you're going to get essentially 5/9 millimole of X in the aqueous and 40/9 millimoles of X in the organic. And finally, step 5, plugging back into the molarity equations, the molarity of X in the aqueous layer will equal the millimoles, 5/9, over the milliliters, 50. Millimoles per milliliter gives moles per liter because the milli cancels. And the molarity of X in the organic layer is the other mole value we found, 40/9 over 20 milliliters, because we combine the two 10 mil fractions. Once again, milli cancels out to give moles per liter. So you can solve those out explicitly and you'll get some decimal values. So overall, if you're given an original concentration of some solute, and then you do an extraction, these steps are those that you follow to find the final concentration in each phase after n number of extractions, right? We first write the molarity equations. It's just moles of X divided by the volume of that phase. And then we find the fraction that remains in the original phase after n number, or in this case, 2 extractions with 10 mils of diethyl ether. We found that to be 1/9 remains and 8/9 partition into the organic phase. Next, you simply find the total moles of X and then multiply the fraction of each phase, 1/9 and 8/9, by the total moles to get the active or the current number of millimoles of X in each phase. Right, you can stick with moles or millimoles, it doesn't matter, but when you divide the millimoles by the volume in milliliters, that will give you the final molarities. So the final question here dealing with extractions is, which of the following would extract the largest percentage, which means we want to have the lowest amount of X remaining or have the smallest Q value. And your options are all using a total of 30 milliliters of diethyl ether. Okay, you could use 30 milliliters of diethyl ether all at once, meaning n equals 1, or you could use diethyl ether twice in 15 mil fractions, or you could use it 3 times in 10 mil fractions. And the amount that is always most efficient is using the smallest volumes the largest number of times. Because when we increase n, remember that Q decreases exponentially. And so the smallest percent of solute, or X, will remain. In the aqueous layer, the majority of X will go into the ether. So if you have the same available solvent to use total, 30 mils, it's always most efficient, and you'll extract the largest amount of solute if you do the largest number of extractions, or maximize N while minimizing the volume, V2. So for more practice with liquid-liquid extractions and separation concepts in general, you can visit Unit 2 of my analytical course guide at chemguides.com.